Hey, I'm Jonathan Wright, and this is my lab report on circuits. So the goal of this experiment is to analyze RC, resistor, capacitor, and DC circuits through understanding of currents and energy, and the key results we got is that RC, resistance times capacitance, is 6 predicted versus the actual result, like from actual data, being 6.58. So the first key concept here is a loop rule, which just says that you can make any loop in a circuit, and as long as you understand the way that the current is flowing through the circuit, the net result will always be zero for the changes in voltage across that loop. And then, yeah, you just generally understand RC circuits, knowing how resistors act in series where they're just added together versus how they are in parallel, which is 1 over R1 plus 1 over R2 equals 1 over R equilibrium. And capacitors, they just do the same thing with reverse. And also current conservation, the current as you go through a circuit stays the same. So part one of the experiment involved this relatively simple circuit where you had 1 ammeter and then 2 resistors hooked up to 2 batteries. First you had to predict the current, which I got 0.02 amps, which then matched what I got in the results in the bottom right. And then from there I had to go through with a voltmeter at different points in the circuit, each of those A through H, and then make that graph that you see in the top right for how you start at the top of potential with 3 volts from those 2 batteries, and then after that you consistently go down because of the 2 different resistors at point C and point E respectively. So part two of the experiment started with calculating the resistance of the different resistors in a different method by just going through the voltmeter and going and getting delta V, and then so from there obviously delta V equals I times R. So if you know delta V and you know the current, and then so from there you can calculate for the resistance even without manually inputting the resistance of the resistor. And as you can tell there from the bottom right, I got very close to the actual results. And then the second image there on the top right, that's dealing with making an ammeter connect to both sides of that 100 ohm resistor. And so the reason that the current increases there to 0.06 is because you can sort of make a loop that avoids that first resistor entirely, the 100 ohm one. And so therefore delta V 3 volts equals 47 ohms times the current. Like if you make that loop, that doesn't involve the resistor, and so from there obviously you get 0.06 amps. So part three, this is the big part where you first do what's on the left, where you charge a light bulb up along with a different capacitor and a 9 volt battery. Charge that up for a 10 ohm light bulb, then time its discharge. Where you do what's on the right, where you just get rid of the battery and have the capacitor charge the light bulb. And so I put the data there up top for those results. And then after that, you hook up a 30 ohm light bulb to the same system as before, and then you measure the voltage as time increases for the discharge, so that you can understand the experimental RC through the equations that I showed you on the right, because you plot natural log voltage with time. That gets you the slope being negative. So that should get you negative T over RC. Ln voltage. So that means x-axis negative T over RC, and then T is our x value. So negative 1 over RC is your slope. And so you solve for RC there. So the discussion here, there's 2 main questions I'm supposed to be answering. First of all, if you're doing this lab in real life with the actual ammeter, then there'd be a difference in voltage with that ammeter because it's going to have some resistance. And for the second one, if you used a real battery to charge a real capacitor, it would take a lot longer because resistance problems.